Thank you. Because Gina gave a talk about the collapsibility number of complexes last week, so I will continue to introduce new results about the collapsibility number of certain simplicial complexes. So let me remind you the definition of decollapsibility. So we are given a simplicial complex with vertex at V and some integer d at least 0. Then we call a face of X is free if it is contained a unique maximal face. And an elementary decollapse is an operation to delete this free face sigma and all faces containing sigma. And we call X is decollapsible if there is a sequence of elementary decollapses to delete everything from the complex. So at the end, we will have a void complex, which is a complex on empty set. So there's nothing. And we define the collapsibility number of a complex by the minimum integer d, where X is decollapsible. And this decollapsibility is hereditary, which means if X is decollapsible, then X delete a vertex is also decollapsible for any vertex. Or indeed, for any induced subcomplex, it's also decollapsible. And actually, any decollapsing sequence for X can be induced to a decollapsing sequence of X delete V. Okay. And this, I hope you remember the D-Lorraine-ness that Gina defined last time. So we are given a simplicial complex X, and this is called the D-Lorraine if the reduced homology of, let's say, Y equals 0 for all I at least D, and Y is an induced subcomplex of X. And this decollapsible property is a somewhat stronger property of this D-Lorraine-ness, because each elementary decollapse is either giving an homotopy equivalent movement, or it's affecting to some homology of dimension at most d minus 1. So if some complex is decollapsible, then it's also D-Lorraine. Here are some examples. So a complex is zero collapsible if and only if it's a simplex. So for a simplex, we can just take an empty set as a free face, and it's contained a unique maximal face, which is X itself. And if the dimension of X is at most d minus 1, which means every face in X has size at most d, then we automatically have the collapsibility number is at most d, because every time we can take the maximal face as our free face. And here is some less trivial one. The clique complex of a polar graph is one collapsible. Here, the clique complex is a complex on the vertex set of the graph whose faces are cliques of the graph. So now the clique complex, so we know for Chordal graphs, they always contain a simplicial vertex, which means a vertex whose neighbor is forming a clique in the graph. So in this clique complex of a Chordal graph, every time we pick the simplicial vertex as our free face, and do the elementary 1 collapse for this vertex. This way we can remove a vertex one by one to delete whole complex. So it is 1 collapsible. And let's say something about the nerve complexes. For a family of non-empty sets, the nerve is a family whose vertex set is that family F, and the faces are intersecting subfamilies of F. And here intersecting means every member has an element in common. Then, so indeed this fourth one, this is where this notion of decollapsibility was introduced. We're going to show that for a finite family of convex sets in d-dimensional Euclidean space, this nerve complex is decollapsible. And more recently, Matoshik and Tensor proved that for a finite family of sets of size at most d, its nerve is decollapsible. And this is where they introduced the minimal exclusion sequence technique that Gina presented last time. And so today we will focus on the collapsibility number of complexes of graphs with bounded independence number. So let G be a graph on V and N be a positive integer. And as usual, we defined alpha G as the independence number, that is the maximal size of an independent set in G. And for each vertex subset, we denote by G big bracket W the induced subgraph of G. And then we define this complex of, indeed it's a complex of subgraphs with bounded independence number as I sub n of G, which is a complex on V, whose spaces are vertex subsets that induces a subgraph with independence number less than n. So if you remember, Gina, at the end of Gina's talk, this was briefly mentioned for line graphs. So here are some simple facts for this I sub n of G. For n equals 1, so independence number is less than 1 means there should be nothing. So it's an empty complex. And for any n which is bigger than the independence number of G, we can put all vertices in our complex. So this complex is a simplex. And when n equals 2, the complex is a well-known complex, which is a clique complex that I defined 2 pages before. So when n equals 2, W is in the complex, means alpha should be less than 2, and that's equivalent to it induces a complete graph. So it should be a clique complex. And our question is this: given a graph class and a positive integer n, find the maximum collapsibility number of I sub n of G among all graphs from the graph class. And this problem was motivated from some combinatorial problem about the rainbow independent sets. So again, let's G be a graph class and n a positive integer. Then we defined f sub G of n as the smallest integer k, such that whenever we take a graph from the class and consider k independent sets of size n from this graph G, and those will be the color classes, then we should find the rainbow independent set of size n. Here, rainbow independent set means it's an independent set, and each vertex can be colored by distinct colors. And the problem here is to find this f sub g of n. And I will tell you how this problem and the previous problem are related. So this is a very special case of Kalaim-Meshulam's topological color-Hartley theorem. So it states that if X is decollapsible, then for any d plus 1 set that's not a face of X, there exists a rainbow set that is not a face of X. So using this, we know that if C sub g of n equals D, then f sub g of n is at most D plus 1. So these VI's here will be the independent sets of size n, which will not be contained in the I sub n of G, and the rainbow set will be a rainbow independent set. Rainbow independent set is, so there, let's say I1 to A1 to AK be independent sets of size n in G. Let's say K is less than n. No, sorry, larger than or equals to n. Then the R is a rainbow independent set if, say, R equals to some x1, xi1 to xil, if so each xi j comes from the set A I J.
I wonder, can we collect? I mean, can we choose more than one vertex from each cluster?
No, just one. Yeah, they should be. The indices should be all distinct. Is it clear?
In the specimen of the two of the VIs and the color class, what's the VI?
Yeah, these VIs are color class, and no, this is this theorem itself is somewhat more general. So just given any complex, we collect the D plus 1 sets that are not faces of X. Then there is a rainbow set that is not a face of X.
So R is like, you take one element from each VI.
Yes.
And the collection of them is not an X.
So, but your color classes don't need to disjoint or anything.
So as a conclusion, it doesn't have to be disjoint. It can overlap.
So the way you defined it here, then no, n is smaller than okay, right.
So for your question, there's it's a little bit tricky that this theorem indeed it's something about some matroid and the complex, and this is a version of when the matroid is a transversal matroid. In that case, these sets should be disjoint. But even if they are not disjoint, we duplicate these vertices as many as it appears in the number of colors that is contained. Then the collapsibility number is still same. It's just a like homotopy equivalent to the original complex. So in that way, it doesn't have to be disjoint. Yes.
Xi up to xi1 up to xij or whatever it is, different there. Are they distinct? So does the size of R have to be at least d plus 1 in the theorem?
So, just finding some partial rainbow set that is not contained in X. If we can find a partial rainbow set that is not in X, then we can add any element from the remaining colors to make the full rainbow set.
Is R a heating set, or does the size of R have to? Does there need to be like?
What this theorem says, when these are all disjoint, then this R is the independent transversal. So, not independent.
So R contains one element from each.
But do they have to be distinct elements?
No.
Okay, that's what I wanted to know.
Some elements may belong to many.
Yeah. Okay. So in that notation, something xi1 might equal xi2.
No.
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 No, in this definition, they should be distinct.
Oh, really? The
Yeah.
theorem.
In the theorem.
Wait. A rainbow set is different from a rainbow.
That's problem because we are looking at I sub n of G, this complex, which is alpha of GW is less than n. So suppose we have some A1 to D plus 1 that's not in this complex, which means they are containing some independent set of size n. And then we find some rainbow set. They don't have to be disjoint. Then we will find a rainbow set which maybe contain. So here's the mechanism. So we have these sets, they may not be disjoint, but let's say this is complex X, then we construct some X prime so that this A1 and AD plus 1 can be disjoint. To apply this theorem, this theorem is for transversal matroid, partition matroid. So this is how Aharoni did. So if some vertex is contained in two different sets, then we duplicate this vertex to in the complex, so that initially it was overlapping, but in X prime we can make this set A1 to AD plus 1 be disjoint. Let's say prime.
So I really just want to know what the word rainbow means.
Rainbow
without independent, so just rainbow set in general.
Yeah. So
I guess for each VI you pick 1 or 0, and then take a union.
Okay.
Yeah. So that's right.
Right.
For each VI you take
I see.
1 or 0 elements.
So you.
Okay. So
you're not taking any of the VIs more than once.
No.
No.
You're
Because some elements may belong to many, but.
So
we are having a set.
Okay. Yes.
Okay. So we are having a set so that we can color each vertex in distinct colors.
Right. So it doesn't need to hit all of them.
Yeah.
Okay.
I still don't understand in the theorem what
set is. And this, just in the conclusion of this theorem, you have the set R. It doesn't have to have v plus 1 elements. It just has to have one element from each vi.
Not even.
Not even like maybe 0 or 1 element from each.
Then why don't we?
Or more than one. But the point is that
Yeah.
we can map.
Okay,
Well,
can you
just
write
apply
down the
that
definition
set
for
of
rainbow
sets.
sets?
But then we
Yeah.
can.
As it's applied in this theorem.
Yeah, but the thing is, it's not in X when it contains independent set of size. Right? It contains independent set of size n.
X
Right.
here, though, is just any complex with.
So subset of rainbow set is rainbow set.
But not necessarily. But a subset of the set that's not in X.
So
like
R is not in X, so therefore it contains an independent set of size n. And
Okay.
this independent set is a rainbow set because it's a subset of rainbow set. Right? So you have a set of size n, which is independent, and and it covers everything.
But why?
I think that's what I understand.
So what do we need to be disjoint to apply? So when you apply the independence complex, the first thing always.
Disjoint.
Yeah, but we don't need to be disjoint, I think. To me,
It
it's
just
apply.
like it follows immediately.
Yeah.
Okay.
So we have a ground set, and we are considering some number of sets, not necessarily be disjoint. And then a set is a rainbow set with respect to this family of size k if there exists some indices I want to distinct indices. I mean, first, X is a set of size k, and second, there exist distinct indices. Let's say X equals I, such that X equals some AI1 to AIK, and AIJ is contained in capital AIJ.
Okay.
So in other words, you can color the union of A1 to AN by one of 2 m colors, so that every element is like.
So
Right.
so it means we are meeting k distinct things from the family.
Yes,
Okay. Yep.
from different color classes.
I don't like the word color class at the end of this choice, but yeah, okay.
Okay, here are some known results. I mean, this is the most classical result in this direction. If we are considering line graphs of bipartite graphs, then Fn equals to 2n minus 1. And later, this Aharoni, Holzman, and Jiang also proved the collapsibility version of this theorem, showing that Cn equals 2n minus 2. And indeed, they proved somewhat more general things for something similar to this definition of I sub n of g, but here is they did some mn of g, which is a complex on H sets, where the bases are H subsets that has a matching number less than n. And they proved some more general thing for fractional matchings. And this is a special case of it by knowing that the matchings and fractional matchings have same size in bipartite graphs. And with Aharoni, Briggs, and Gina Kim, we have several more results. So this first easier results are for the class of graphs with no complete graph on m vertices, then Fn equals this Ramsey number, Rm, n. And for the class of all k collapsible graphs, it's Fn equals to k times n minus 1 plus 1. And it's easy to see the corresponding results for collapsibility numbers. So for km3 graphs, Cn equals to Rm, n minus 1. And for this k collapsible graphs, Cn equals to k times n minus 1. And each of these results, so we can easily see that the faces in this complex must have size less, at most this. For example, in km3 graphs, if we have more than this many vertices, then by the Ramsey theorem, it should contain either km or independent set of size n. For k collapsible graphs, I will leave it as an exercise for students. So next one is for Chordal graphs. Then so Fn equals to n. And this is also easy by looking at simplicial vertices in each step and greedily take the rainbow independent set. But we can also have the collapsibility result, even though it's more complicated. So first, we need to define what is the link complex. Given a simplicial complex X and some simplex sigma in X, we define the link of sigma in X as a complex whose faces are faces of X that is disjoint from sigma, and together with sigma, this tau union sigma is a face in X. So note that this complex is a complex on the vertex set of X minus sigma. And the tensor showed that for every vertex of the simplex, the collapsibility number of X is at most the maximum of collapsibility number of X minus V and collapsibility number of link of V plus 1. And using this lemma 1, we can show, and also using the property of simplicial vertices, we can prove for Chordal graphs, I sub n of G is always n minus 1 collapsible. So first, we find the simplicial vertex. Then this link complex is indeed same as I sub n minus 1 of some induced subcomplex, induced by the vertices not in the closed chamber of V. Then just applying this tensor's lemma, so by induction on n, we can easily know n and the number of vertices. We know this I sub n of G minus V is always n minus 1 collapsible, and this link complex is some complex I sub n minus 1 of some other Chordal graph. So it's n minus 2 collapsible, and we plus 1 here. So we will have, so we will have a Cn equals to n minus 1.
So the lemma A is for any complex X?
Yeah, for any complex, its collapsibility number is at most this for every vertex. Okay. And our main contribution is on these graphs with bounded maximum degree. So here, a combinatorial result we obtained is Fn is between this number and this number, and the lower bound comes from the T power of the cycle of length t plus 1 times n. So the power means we have a cycle of length t plus 1 times n, and in each vertex, so there will be consecutive vertices in the cycle. We connect this vertex and the vertex in distance t from this vertex. So up to t. And in this graph, we can obtain this bound. And for the upper bound, it comes from the results for k-colorable graphs, because if a graph has maximum degree at most k, then it's k-colorable unless it's a complete graph on k plus 1 vertices or an odd cycle. So for that special cases, we can handle it. So we can prove this upper bound. For n small values of n, we could prove this lower bound is indeed the right number. So f2 equals to the ceiling of k plus 1 over 2 plus 1, and f3 is 2 times k plus 1 over 2 plus 1. And we conjectured that in general, fn equals to this lower bound plus 1. And then we can ask some, so it's natural to ask this question. So can we solve this conjecture using the collapsibility numbers? We hoped so, but unfortunately, the answer is negative because of this example. So this here we have a degree, it's a 3 regular graph on 20 vertices. And here we can compute the homology of I sub 8 of this graph, and it's not vanishing in dimension 15, which means it's not 13 collapsible, it's not even 15 collapsible. Yeah. And yeah, because of this example, the answer for this question is no. But our main result is to give a partial solution for this conjecture, still using some collapsibility number result, but maybe not for this I sub n of g, but some special subcomplex of I sub n of g. So here are our main results. So we proved this corresponding collapsibility results of this second part of this theorem. And also, so we prove this for some subclass of this class of graphs with maximum degree k. So we consider claw-free graphs with maximum degree k. Then here, whenever we take an independent set of size n-1, then certainly this A is a simplex in I sub n of g. And then we look at the link complex of A in I sub n of g. Then it is this k times n-1 over 2 collapsible. And this can give a partial solution for this conjecture, showing that this is true for claw-free graphs when k is even, and almost true for when k is for claw-free graphs when k is odd. So I will explain how we derive this from theorem 2 later. And let me first describe the proof of theorem 2. to prove theorem 2, we introduced some lemmas, 2 lemmas indeed, and what we need is 3 lemmas, but one is this lemma A from here, tensor's lemma. Maybe let me write down this. Think of x, y. So first lemma is this, tensor's lemma. And the second is by applying this lemma A repeatedly, we can prove this lemma for any phase in X. We give some linear order on the vertices of sigma and define sigma I as the subset of sigma consists of first I vertices of sigma. Then if we know the link of sigma I in X minus Vi plus 1 is D minus I collapsible, and link of sigma K in X is D minus K collapsible, then X is decollapsible. I know this is complicated, but what we can prove this lemma is that this proposition. So first we define what is missing phase. Given a complex, a missing phase is a set of vertices whose all of its proper subsets are phases of the complex, but this set W itself is not a phase of X. This is a missing phase. For example, empty triangle or empty tetrahedron in the complex is a missing phase.
Minimal non-phase.
Yeah, minimum non-phase. So then using this lemma, we can prove that if all missing phases of X have size at most D plus 1, then this X is D times number of vertices over D plus 1 collapsible. Maybe I will write it down also. All the missing phases. And then using these two, we can prove that I sub 2 of G is at most K plus 1 over 2 for graphs with maximum degree K. So we use induction on V. So first we apply this lemma A and have this relation. Then we need to look at this induced subcomplex and this link complex. But by the induction hypothesis, we know for this complex, the bound will be this. So we only need to look at the link complex. But you know, I sub 2 of G is the clique complex. So in the clique complex, all missing phases have size at most 2. And this is especially called a flag complex. So we can bound the collapsibility number of the link complex in terms of the number of vertices in the link. But because we are looking at the graphs with a degree at most K, and if you look at the link of V in the clique complex, then the vertices in the link will be the neighbors of V. So we can bound the number of vertices by K. So it will give us this bound. So we are done.
I'm trying to understand the link of I2 of G. So I2 is the induced by the set
Yeah.
Clicks of size.
Yeah, I2 of G is a click. Spaces are clicks. So if you look at the link, then
you will collect.
So the vertices in the neighbor of V are in this link complex, and all clicks in this neighbor is a face in the link. So for example,
But I2 doesn't have any.
I2 doesn't have any triangle, isn't it? Or
For example, if
I have this graph and let's say this vertex is V, then the I2 of G, which is a click complex, is V, this complex. And then we look at the link of V, then so it's a complex on these three vertices, so it will be 1, 2, 3, they are all in the complex, and 2, 3 is also in the complex because this triangle is a face. So it's precisely the click complex on the neighbor of V, open neighbor of V. So we are done. And now we will need one more lemma. And I also understand this is very complicated, and because I don't have much time. So here is some. This is exactly what we need to solve my main result. So given a simplicial complex on, with vertex at V, and take any subset B of V. So forget about this linear order. So if for any partition of set B into two parts, B1 and B2, if you look at the link of B2 in the induced subcomplex on V set minus B1 is D minus B2 collapsible, then X is D collapsible. And now we are ready to prove theorem 2. So first, because we are looking at the link of an independent set of size n minus 1, so if you are looking at the link, then every vertex in the link should be adjacent to some vertex of A. And because we are looking at clue-free graphs, so we can partition these vertices in the link into two parts, one having one neighbor in A and the other having two neighbors in A. And then this set B will be the set B in this lemma, this B. So this now the link complex is a complex on U union B. And then we take, to apply this lemma C, we take any partition of B into two parts, B1 union B2. And then we will show that this link of B2 in this induced subcomplex is this number minus size of B2 collapsible. This is our claim. And if this is true, by applying lemma C, we can say the link of A in I sub n of G is this number collapsible. So it's enough to show this claim, it's true. And let's say this complex equals Y. And it's easy to see that this complex is indeed same as I sub n of G delete B1. The link of A union B2 in I sub n of G delete B1. And then take some missing face. So we want to apply this proposition B. So take any missing phase. Then this is a missing phase because there is some independent set of size n that contains tau and is contained in tau union A union B2, because we are looking at the link of A union B2. So we have this independent set of size n, and this middle part is a missing phase. Then let's take I such that the intersection of I and A is maximal. Then it's easy to see that for any vertex in this red part, A set minus I should have two neighbors in the rest part of I. So I minus A. Because unless we can either delete one vertex from I and put one vertex from A, or if this intersection has size 1, then just exchange the vertex from this red part and the vertex that is adjacent to that vertex. So we exchange it, then we can construct other I prime with I prime intersect A is bigger. So by the maximality, we can assume this equals 2. So all vertices in this red part should have two neighbors in I. Then we can do some double counting by summing up all these intersections. Then for any vertices in this red part should have two neighbors. So we will have the size of A equals n minus 1, and we need to subtract the size of A intersect I and multiply 2. On the other hand, the edges from here to there. So remember, this B2 is a subset of B, where B is a set of vertices that has two neighbors in A. So we will have 2 times the size of B2 intersect I. So all vertices in this intersection will have two neighbors in A, but it cannot be this part, so it will have neighbors in this red part. And all vertices in tau is contained in U, which is a set of all vertices having one neighbor in A. So we just multiply 1 to the size of tau. And from this equation, equality, so we can obtain the size of tau is actually 2, meaning that this complex Y, this complex, is a flag complex. So now we have Y, a flag complex, then we can apply proposition B. So the collapsibility of a Y is bounded by half of the size of U. And we can bound the size of U by the double counting again. So we count all the sum of the size of neighbors of A for all vertices of A. Then, so it will be the size of U plus 2 times size of B, because U has one neighbor in A. B, every vertex in B has two neighbors in A. And then here we are using the bounded degree condition. So every vertex in our graph has at most k neighbors. So this is bounded by k times size of A, which is n minus 1. Then U is bounded by this number, and together with this inequality, we can obtain the Y, which is this link complex, is k times n minus 1 over 2 minus size of V2 collapsible. So this completes the proof. And now I need to explain how can we derive this corollary from this theorem. So this corollary means for any clue-free graph with maximum degree k, whenever we collect this many independent sets of size n, then there is a rainbow independent set of size n. And this is again by the collapsibility theorem in a different way. So we first apply the induction hypothesis to find a rainbow independent set of size n minus 1. We still need one more. Then, so subtracting n minus from here, we still have this many color classes that is not a phase in the link. Then, by applying the Calafar-Hawley theorem, the Calais-Mechoulam theorem, we can find the rainbow set R prime that is not a phase in this link complex. And all of these colors are distinct from the colors in R. So R union R prime is a rainbow set that is not a phase in I sub n of G, meaning that it contains a rainbow independent set of size at least n. So let me conclude my talk with two open problems. The first, so we proved this I sub n of G comma A, the link of A in I sub n of G is k times n minus 1 over 2 collapsible for clue-free graphs with maximum degree k. But our conjecture is we can have the same result without assuming the clue-freeness. And the second question is, what is the best bound for the collapsibility number of this original complex I sub n of G for this class dk, the graph class of graphs with maximum degree k. So this example I showed you is the dodecahedron by taking the k disjoint union of k copies of this graph, we can obtain when k equals 3. There is some, this example gives an example that I8k of G is not it's not 17k minus 1 collapsible. This could be minus 2. But so it still does not meet this conjecture, because when k equals 3, this conjecture means 3, in this case, 2 times 8k minus 1. This is smaller than 17k. But it's also smaller than this bound from the k colorable graph, because this gives us 3n, but this is far from 3n. It's closer to 2n. So I wonder what is the best bound for C n for this graph class. And this is the end of my talk. Thank you.
Okay, thank you. Any questions?
So do you think that the collapsibility number is still k plus 1 over 2 times n minus 1 plus 1 when n is small, say n is 4 or 5? Because you say there is example showing that you have check inequality when n is at least 8 or something. So what happened with small n?
We haven't tried. We just know for n equals 2 and n equals 3. You know, we had these results. So for n equals 2, I showed you. For n equals 3, we have this result, but the proof of this uses all of these lemmas and it's quite complicated. So I didn't show you. But even from n equals 3, it's super complicated, so we haven't tried for n equals 4 case.
Can I ask you something about this theorem too? I probably missed the definition. So link of ing of A is like in the complex consisting of all graphs whose alpha is less than n. You're looking at the all in the subgraphs containing particular independent set A, right? And
So
then
this link complex
what is it? I try to imagine it. And you can never, so you that means you just want to look at the neighbors, right? In terms of the,
yes, maybe.
yeah, so is that correct? Just,
Yeah,
it's
so
just the complex of neighbors? Or neighbors?
it's a complex on neighbors, but
But neighborhood itself may have an independent set of size bigger than
yeah. So
n,
for
so
example,
that's a danger.
if this is my independent set of size n minus 1,
Yes.
and we look at the neighbor of it, but if there are 3 vertices that are not adjacent to these vertices but only connected to these 2 vertices, then this triple is not living in the link.
I see, because then independent
Yeah.
number will be
Together with this, they will form a independent set of
Ah.
size.
I see.
By the way, this is also tied by the example. This example. I mean, tied for k even.
I mean, if you replace closely by K1 T3 or some T, does your technique go through for some small values of T?
We have thought about it, but seems like it's not. It doesn't behave well like this somehow.
Any other questions?
Is there any other graph class to be considered?
I don't know if it's an interesting question, but here, I mean, in this paper, we also proved for if we forbid instead of km, if we forbid km minus 1h, like a diamond, then this fn is also, for that graph class, is also bounded. But we don't know the exact number for that class. But it's something between some Ramsey number and some larger Ramsey number, so I don't know if it's a good question. Other than that, well,
So the first one gives a corollary of a rainbow clicks, right? Like if you have a many Ramsey number, many clicks, then
yeah, maybe just taking complements.
then you can find the rainbow click. But rainbow click of size n, probably. Sure. Any other questions? Okay, if not, let's thank the speaker again.